Hi! In this video, you will learn what complex numbers are and why we need them. We will see that complex numbers can be used to solve certain second-order linear differential equations. For instance, consider the differential equation y double prime minus y equals 0. If we try to find a solution of the form e to the power r times x, where r is a constant, we obtain that y prime is r times e to the power r times x, and y double prime is r squared times e to the power r times x. We substitute this into the differential equation to find that r squared times e to the power r times x minus e to the power r times x should equal 0, or r squared minus 1 times e to the power r times x should equal 0. Since the exponential function is positive for all values of r and x, we conclude that r squared minus 1 should be 0, which leads to the solutions plus or minus 1. This implies that both e to the power x and e to the power minus x are solutions of the differential equation y double prime minus y equals 0. This leads to the general solution c1 times e to the power x plus c2 times e to the power minus x, where c1 and c2 are arbitrary constants. Now consider the differential equation y double prime plus y equals 0. If we try to find the solution of the form e to the power r times x, in the same way we find that r squared plus 1 should be equal to 0. This equation clearly has no solutions. However, the differential equation has solutions. It is easily checked that both cosine x and sine x are solutions of y double prime plus y equals 0. In order to find these solutions of the differential equation, we introduce a non-existing solution of r squared plus 1 is equal to 0. Later we will see how this helps to solve the differential equation y double prime plus y equals 0. We define I to be an imaginary number with the property that I squared is equal to minus 1. Now we define a complex number z to be a number of the form x plus I times y with x and y real. The word complex indicates that the number exists of two parts. X is called the real part of z, and y is called the imaginary part of z. Now r is equal to I is a solution of r squared plus 1 is equal to 0, and r is minus I too, because we have that r squared is equal to minus I squared, which is equal to minus 1 squared times I squared, which is equal to minus 1. The real and imaginary parts of a complex number are similar to the coordinates of a factor in R2. This implies that addition and subtraction are defined component-wise. For instance, minus 2 plus 3i plus 3 minus 4i is equal to minus 2 plus 3 plus 3 minus 4 times I, which is 1 minus I. And 7 minus 2i minus 2 minus 5i equals 7 minus 2 plus minus 2 plus 5 times I, which is equal to 5 plus 3i. Similar to factors in R2, we can represent complex numbers in the so-called complex plane. The horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. This is sometimes called the Argand plane. Besides addition and subtraction, it is also possible to define the multiplication and the division of complex numbers. The product of two complex numbers is defined by expansion as shown. Here, I squared equals -1, which leads to the real part, a times c minus b times d, and the imaginary part, a times d plus b times c. In class we will see how to deal with divisions. Now it is important to realize that, in terms of complex numbers, every second-degree polynomial has two roots, not necessarily distinct. In class you will see how this works. See you then. Bye.